In this video, we're going to talk about energy of the simple harmonic oscillator. So we want to know the components of the energy, kinetic component and potential component. Okay, so let's recall that we have this model system, which is a block with mass m that is connected to a spring. There is no friction between the surface and the block, and when the block is extended from its equilibrium position so that the spring is stretched by an amount x, it feels a restoring force Fs. And remember that this Fs is equal to minus kx. Since I have mu k is equal to 0, isolated system, that means in the process of this oscillation of the block, energy, total mechanical energy must be conserved. So delta E must be equal to 0. Total mechanical energy is conserved. The only force that causes this motion is the restoring force, which is a conservative force. And remember, it's derivable from a potential energy. So using the work potential energy theorem minus delta U, if I have the change in potential energy from x equals 0 to x equals x, it's the minus the integral the force dot product with the displacement it causes. And because I have a force in minus I hat direction and the displacement is dx I hat, the integral from 0 to x gives me integral from 0 to x kx dx, which is the change in potential energy between x and 0 is equal to 1 over 2 kx squared. And similarly, so I have, because the potential energy is 0 at x equals to 0, kinetic energy 0 joules, kinetic energy component is also present. It's equal to 1 over 2 mv squared. So if I write the total mechanical energy of the system, it's kinetic plus potential. It is 1 over 2 kx squared plus 1 over 2 mv squared. Potential energy plus kinetic energy. Now I want to recall the equation of motion. Equation of motion was x double dot is equal to minus omega square x, and the solution to this equation was x of t is equal to a cosine omega t plus phi, and the velocity as a function of time is minus a omega sine omega t plus phi. It's the derivative, so this is equal to x dot, remember. So if I write the kinetic energy of this oscillator, kinetic energy is equal to 1 over 2 mv squared, which is 1 over 2 m a squared omega squared sine squared omega t plus phi. And if I write for omega squared, remember this omega was defined as omega squared is equal to k over m. If I write for omega squared k over m here, so here I substitute k over m, the kinetic energy component becomes 1 over 2 m k over m a squared sine squared omega t plus phi. So the m's cancel. Therefore, the kinetic energy component is equal to 1 over 2 ka squared sine squared omega t plus phi. And if I write the potential energy component, it is 1 over 2 kx squared. It's 1 over 2 ka squared cosine squared omega t plus phi. And if I write the total mechanical energy of the system, total mechanical energy is kinetic plus potential. It will be equal to 1 over 2 ka squared sine squared plus cosine squared of omega t plus phi. So this is going to give me 1. So the total mechanical energy of the system has to be 1 over 2 ka squared. So this is what I find. It's a constant, and throughout the motion the total mechanical energy is conserved, and it must be equal to 1 over 2 ka squared. Now using this relationship between potential energy and kinetic energy, I want to look at this equation 1 over 2 mv squared plus 1 over 2 kx squared. So throughout the motion, these should add up to 1 over 2 ka squared. So 1 over 2's cancel. I find that mv squared is equal to ka squared minus x squared. In other words, v is equal to plus or minus square root k over m parentheses a square minus x square. Square root k over m is omega, so the velocity must be equal to plus or minus omega square root a square minus x square. So basically I can write the velocity as a function of the displacement from the equilibrium position using this, and I notice that v is equal to v max, which is a omega, when x is equal to 0. So I reach the maximum kinetic energy when x is equal to 0. Now I want to plot kinetic energy and potential energy as a function of time and as a function of displacement. So if I start at maximum kinetic energy 1 over 2 ka square, you see the orange color is kinetic energy. That means at this position I have x is equal to a. So the kinetic energy is 0, so it has reached its maximum point in the oscillation, and I find that the kinetic energy has to be 0. It's the maximum restoring force that I feel. It will be equal to minus ka, and at this point the potential energy is maximum. Then I see that I go from x equals a to x equals to 0. At this point the kinetic energy is maximum, the potential energy is 0 because there is no restoring force. Then I go to x is equal to minus a. At this point again I find that the potential energy is maximum. I feel the maximum restoring force ka, and the kinetic energy is 0. And then I go back to x equals to 0. At this point the potential energy is 0, kinetic energy is maximum, and then I go back to x is equal to a. So you see I started at t is equal to 0 at x equals to a, and at t is equal to 1 period I'm back to x is equal to a. So 1 full period. So you can see that the kinetic energy and potential energy oscillations are basically following a period of t over 2 instead of t. Okay, now if I look at kinetic energy and potential energy as a function of x, so at t is equal to 0 I was at x is equal to a. At that point the potential energy was maximum, and kinetic energy was minimum. The particle velocity is 0. I feel the maximum restoring force. Then I go to the maximum kinetic energy, minimum potential energy. When does that happen? When T is equal to T over 4. And then I go to zero kinetic energy and maximum potential energy again. That's on the other side of the oscillation. So that's half a period. So this is T is equal to T over 2. Then I go back to maximum kinetic energy and zero potential energy. That's 3T over 4. Then I'm back to x equals to A in one period. T is equal to T. And notice that throughout the oscillation, kinetic plus potential energy is here. It's a constant. It is 1 over 2 Ka squared. So this has to be kept constant throughout the oscillation. This is true both as a function of time and as a function of x. So the maximum mechanical energy, the maximum kinetic energy I have, or the maximum potential energy I have, is equal to 1 over 2 Ka squared, which is the total mechanical energy of the system. And writing this energy conservation for this isolated system also allowed me to obtain the velocity of the oscillator as a function of x. Now, the simple harmonic motion that we study here is basically a very basic concept, and it will apply to many different physical phenomena. So the simple harmonic motion analysis applies to many cases where the equation of motion is of the form x double dot is equal to minus omega square x. So you know how to solve this differential equation. You know the energy components associated with this equation. Therefore, you know the solution to many physical phenomena that has the same equation of